Well, before we get into the typical exam problems, we have some unfinished business from the reviews and examples part of this lesson. Today we want to talk about the impulse momentum principle, and that's written this way, that the impulse imparted to a body is given by the change in momentum, delta P being a change of momentum. Well, change of momentum is actually given by the force times the change in time, because impulse, the way you measure impulse is the amount of force you apply over a period of time. So since impulse is equal to F delta T and F is equal to delta P, then these two things must be equal. So I can write from this equation now that the momentum of a moving object is given by P is equal to M times V. But we just saw a little while ago that I can write this impulse F delta T and equate this to M delta V. It's a change in velocity. When you impart impulse to a body, it changes its velocity. So F delta T is a measure of the impulse, and there's a change of momentum. So this can be written as M times the final velocity minus the initial velocity. Now for fluid flow, there is a flow rate. And so what I'll do is I'll divide both sides of this equation by delta T and talk about F is equal to M over delta T times V2 minus V1. Well, M over delta T is the same as M dot. So I have F is equal to M dot times V2 minus V1. And I can write this yet another way, since I remember from earlier work that M dot is equal to rho times A times V. I can write here that F is equal to rho times A times V multiplied by the change in velocity delta V. And rho times A times V, or rather A times V, recognizes Q. We've had that before, flow rate, mass flow. So this becomes Q times rho times delta V. So that's the measure of the force and how the force affects the flow in, say, a pipe. So if we were to put this all together now, take this equation and generalize it, we'd say that the sum of the forces using the impulse momentum principle is given by Q2 times rho 2 times V2 minus Q1 times rho 1 times V1. That's just a manifestation of the same equation. All right, we're going to be using this as a way of calculating the forces that are caused by a bend in a pipe. We just saw that the impulse momentum principle told us that the summation of forces is equal to Q2 rho 2 V2 minus Q1 rho 1 V1. Now, when you have a pipe, let's say we have a pipe that does something like this, and it has an entrance velocity V1, exit velocity V2, area A2, area A1, pressure P1, pressure P2. It gives rise to a very interesting situation, because as the fluid enters the pipe, it's deflected in this direction because of the fact that there's a deflection angle to be, let's call this angle alpha, that exists within this pipe. There's a bend and there's an angle alpha. So because of that, you have to equate forces. We have P1A1 is the force entering. We have a deflection force that's caused by the pipe bend. And we have, because of the angle alpha, we have to include that in our calculations. So you'll find that it's a very simple equation that involves the entrance velocity, the exit velocity, you have an entry force, you have a deflection force, and when you sum these together, you can end up showing that the force caused by the bend in the pipe, F sub x, looks something like this. It's P2A2 cosine of alpha minus P1A1 plus Q times rho. Let's assume that Q2 and rho 2 and Q1, Q2 are the same, rho 1, rho 2 are the same. We have Q2 times V2 cosine of alpha minus V1.